Good afternoon. Today we are here to learn about solution of second order differential equation using fourth order Runge-Kutta method. This is by Professor Tanuja Date from Electrical Engineering Department, Kekewag Institute of Engineering Education and Research, Nasik. Now, for solving differential equations, we have already studied fourth order Runge-Kutta method, but we have used it for solving first order differential equations. If you want to revise the method, you can go to this YouTube video where the fourth order Runge-Kutta method is explained nicely for solving first order differential equation. You can take this as a revision and you can learn fourth order Runge-Kutta method for solving first order differential equations. Now, how these second order differential equations look like? If we see d square y by dx square equal to x dy by dx plus 2xy, the order of this differential term is 2, and so we say this is the second order differential equation. Just by using Runge-Kutta method, as we have studied, this equation cannot be solved. So for solving such equations, we need to convert this equation into two different functions and then we can solve it. Okay, for example, this d square y by dx square, this will be given as a given second order equation, differential equation, with initial conditions. Most of the times, x0 is a starting point and the function y is evaluated at this point and the value will be given as y of x0. The first derivative term of this, again evaluated at the same starting point, also will be given. Now these 2 points as y of x0 and y dash of x0 are given as initial conditions. So most of the times we have defined along with the second order differential equation, we have initial conditions given as the starting point x0, the first function evaluated at x0 point, and the first derivative evaluated again at the same point as the initial known data points. And we are asked to evaluate as a solution to evaluate the function at a new point, which is x0 plus h. So if x0 is the starting point, the new point at which we are evaluating is displaced by h increment. So we can calculate y of x0 plus h as y evaluated at the starting point plus 1 by 6, 4 different values k1, k2, k3, k4 which are calculated and used in this formula as k1 plus 2k2 plus 2k3 plus k4. So this formula is nothing but formula given by fourth order Runge-Kutta method for evaluating which we have studied for first order differential equation. How to make use of this formula and how to evaluate k1, k2, k3, k4 is to be learned for second order differential equation. Now let us see the steps. If we are given with second order differential equation, first we need to assume a new variable z as dy by dx. So first order derivative term in the equation can be replaced by z, and we will be calling this equation itself as z equal to dy by dx equal to function of xyz. So since it is the first function which we have identified, we will be using this as first function, and the second function which is obtained by replacing now dz by dx at the place of d square y by dx square as the second order term, and rest of the terms given in the equation are transferred on the other side, and we will be calling and obtaining this function as g of xyz. So given equation, second order differential equation, we have split into two functions, f of xyz and g of xyz, by just assuming another variable at the place of first order differential term dy by dx. And so with the initial conditions which we had started with as x0, the starting point, function evaluated at x0, we will be calling it as y0. And the first derivative term evaluated at x0 point, which now becomes z0, because first differential term we are calling as z. So y dash of x0 henceforth we will be calling as z0. Using these three starting points, we can evaluate the function at using x0, y0, z0, multiply it by the displacement h, and we will be calling this as k1. Now in this case, if f of xyz is equal to z, in this case it becomes h times z0 as k1. Now parallelly, we need to also use the second function and calculate L1 as exactly same formula, only replaced by the second function, h into g function evaluated by putting x0, y0, z0. In this case, now what is g? G of this will be all the terms which are obtained from the first equation transferred on the other side. We will put x0, y0, z0 as per the arrangement of the variables, evaluate that function, multiply it by h and store it as L1. Once we have k1, L1 values, we can proceed for calculating k2 next value as h into function evaluated at x0 plus half increment, which is h by 2. Y value will be changed from y0 to y0 plus k1 by 2, which is previously calculated. And for modifying the third variable which we have assumed, we will be making use of L1 value. So z0 plus L1 by 2 will modify z value. Again, as we know, the function is only z. So z0 plus L1 by 2 would be the new value of this function evaluated, multiplied by h becomes k2. Now L2, we will be using same three variables, put in function g, multiplied by h and store it as L2. K2, K3, similarly L2, L3 are calculated at the same x point. If you see x0 plus h by 2, x0 plus h by 2, so we are not making any modification for x variable when we move from K2 to K3. But for y variable, we will be making change by considering the previous k value as well as previous L value which we have calculated. And so y0 plus k2 by 2 becomes new value of y, whereas z0 plus L2 by 2 becomes new value of z. Again, k3 will be calculated, L3 will be calculated by putting it into function g. On the same lines, the last point k4 will be at the final function value to be evaluated at this point x0 plus h. Now it is not divided by 2, so this was midpoint and this is the final data point at which we are asked to evaluate the function. So it will be x0 plus h, y0 plus k3, you don't need to divide it by 2 anymore, z0 plus L3, whatever we have calculated, and then we can also calculate L4 as the last value. When we evaluate y at x0 plus h, we can evaluate by taking the initial value of y at x0 plus 1 by 6 in the bracket, k1 plus 2k2 plus 2k3 plus k4 as the average of all k values divided by 6, and we get the final value y of x0 plus h. Now this is the process where we are using fourth order Runge-Kutta method for solving a second order differential equation. This is first example to actually elaborate how can we solve second order differential equation using this method. Now this is the equation, d square y by dx square minus x square dy by dx minus 2xy equal to 1 as the second order given differential equation. These are the initial conditions. Y of 0 is 1, y dash of 0 is 0. That means x0 value is 0. And you evaluate y at point 1 using fourth order Runge-Kutta method. So first we have to assume dy by dx equal to z, which becomes our first function. Second function will be rearrangement of this given equation where d square y by dx square now becomes dz by dx. So we take this on one side and take all the remaining terms on the other side. So it becomes d square y by dx square equal to 1 plus 2xy plus x square, where dy by dx will be replaced by z. So this becomes now dz by dx or d square y by dx square equal to 1 plus 2xy plus x square z as the second function. So when we say first function is f of xyz equal to z, g of xyz equal to 1 plus 2xy plus x square z. Now henceforth we will be using these two equations for evaluation for calculation of k1, k2, k3, k4 and L1, L2, L3, L4 respectively. And every time while incrementing the variables, the first value of k1 since z0 is 0, y0 is 1, x0 is 0, k1 value becomes 0 because z0 is 0. L1 is now g evaluated, it becomes 1 plus 2 into xy, x is 0 and y is 1, so second term also becomes 0 and the third term z0 is x square z. So since x is 0 and z is also 0, so there is no contribution from these two terms and it is 1 into 0.1 which makes it 0.1. See carefully how the variables have changed their values. x0 changes to x0 plus h by 2, y0 changes to y0 plus k1 by 2, z0 changes to z0 plus l1 by 2. And again evaluate the function to get k2 value as 0.005 and L2 value by putting same variable values into the second function, we get L2 as 0.11. You can cross verify the calculations and do the calculations yourself for verifying the values. Once we get all four K1, K2, K3, K4 evaluated by putting L3 value here and evaluating the function and calculating L4 as well, we can finally substitute them into this equation. Y of 0.1, which is the answer which we are interested in, is equal to y0, which is given to be 1, plus 1 by 6. In the bracket, you will be putting values of K1, K2, K3, K4 by taking appropriate weights for K2 and K3, and we can get this final value as y of 0.1 equal to 1.0053. There is another example which also is solved on the same lines. I will be showing and explaining you how we have split this equation again. The first equation is always dy by dx equal to z, which becomes the first function, whereas d square y by dx square, when we rearrange this x into z square minus y square, becomes the second function. Our h value becomes 0.2 because we are deciding to do all this into single step and calculate k and l values respectively by taking the formulas which are k1 calculated as h into function evaluated, L1 also h into g evaluated at the initial points, and by incrementing the variables respectively for k2, k3, k4 by taking x0 as x0 plus h by 2, x0 plus h by 2 and x0 plus h as the final value. We can continue doing the calculation for all the factors k1 to k4 and L1 to L4, finally substituting them in the formula given by fourth order Runge-Kutta method, and we can obtain the final value y of 0.2 as 0.980146 by substituting all k values as calculated with appropriate weights in the given formula. If you have understood this process, you can try solving these two examples which I have given as homework and with initial conditions, and you are asked to calculate at the unknown data point in both the cases. Respectively, you can calculate h value, you can calculate k and l values correctly and then cross-check the answers. So these two problems are home assignments. You can solve them using fourth order Runge-Kutta method. I hope you have understood this process and the method for solving second order differential equation using fourth order Runge-Kutta method. Thank you. Happy learning.